Today we're going to be talking about developing trust and getting betrayed. And trust is a very important thing, whether it's between people in relationships, companies, processes, or giraffes. And when trust is betrayed, the results can be devastating. A little bit about us before we get too deep into it. My name's Clint Gibler. I'm a Midwesterner living in SF, which is the land of goat yoga and kombucha on tap. I'm a security researcher at NCC Group, and I was once filmed monologuing to a live emu. With me is Noah Badome.
Thanks, Clint. My name is Noah Badome. I'm a lover of fine root beer, a security researcher who pretends to be a director of infrastructure security during the day, and a former Marine. Hoorah!
All right, so a little bit about the agenda. First, we're going to give some overview and motivation for the work. Then we're going to talk about trust as it pertains to company and organization. Then we're going to talk in more detail about development-focused environments, which are the target of this talk. We're going to discuss the architecture of Gitting, which is a tool we're going to demo and release today. Then talk about some mitigations for some of these attacks. And finally, take questions at the end. So if you wouldn't mind holding questions to the end just to make sure we can get through things, we're happy to answer a few immediately and then in a room nearby after. So, all right, so the background is Noah and I were performing a number of network penetration tests over the past few years, largely of development-focused organizations. And a key point of failure we found was this bridging of trust zones, say, between the development and production environment. Oftentimes, this happened because of implicit trust and a lack of guidance around developer and DevOps. So the goal of this talk is twofold. First, we want to discuss how trust relationships between people and infrastructure can be exploited. And then second, present a tool, Gitting, that puts these ideas into a practice. So this tool can be used by internal security teams or consultants to help attack and assess development-focused organizations, or be used as a concrete example to show here's the impact of these types of common issues in practice. So I will pass it off to Noah to discuss trust.
Right, thanks, Clint. So throughout the talk, we're going to talk about several key things, and the first is going to be the role that trust and trust relationships play in kind of the attack and exploitation scenarios that Gitting is meant to highlight. So before we get into that, really, I want to talk about what trust relationships are, right? So trust relationships are essentially the amount of impact two or more entities can have on each other because of the amount of trust and allowance for communication or connection they may have. This can be between people, networks, systems, etc., right? So trust relationships are established on the actual amount of controls, protections, privacy, and security in place, not necessarily the intended amount of trust, right? So you usually see this in the fact that we might say, these two environments aren't allowed to talk to each other, but actually we punched a bunch of holes at some point and they can, right? So when we're talking about trust relationships, we're talking about the actual amount of trust there and not the implied amount. The next is that trust relationships usually exist between trust zones. So a trust zone could be really any areas that might have a different level of secrecy, security, privacy associated with them. So example might be a difference between a public living space and your private bedroom, between a production environment and a staging environment, etc. So one thing to keep in mind is that when we're talking about trust relationships and trust zones, very often security and these restrictions we put between our different trust zones happen to impede some level of function. And instead of maybe designing better processes to utilize that, we tend to invalidate these trust relationships and punch holes in the barriers to get the job done, which can usually result in some significant problems down the road. So this is the list of people and things I trust. And the example here is that whenever we're establishing trust zones and trust relationships, we want to limit the amount of trust to what's really actually required for the relationship to work properly, right? And so when we're talking about trust relationships, they can exist in a variety of forms and types, right? They can be employer to employee, they can be organization to organization, they can be project to collaborator, network to network, system to system, right? So some examples of this might be, as an employer, I trust my employees to come into work, use assets, have access to the building, et cetera, and I trust that they are going to operate in the fashion that we've agreed upon. Another example would be network to network. So I might say that the normal corporate network cannot talk to the production network on any port at all. Or I might say that staging can talk to the production network across a couple controlled ports from specific source IPs, right? These are kind of the examples of these trust relationships in practice. So, okay, well, this is all well and good. We have trust relationships and trust zones, and we know that we sometimes mess them up to get the job done. But what does this really mean? So the thing that tends to get missed is that trust is transitive, inherited, and implicit. So essentially what this means is that if I trust you and you trust something else, functionally, in some ways, I trust that third party. So you see this in the form of, in a person example, if I trust you and I believe anything you tell me, and you believe anything Jenny tells you, and Jenny is a liar, right? I functionally believe anything Jenny says, right? We see this in actual network implementations and production environments when we see things like production trust staging, and staging trusts a small group of release devs who all use a bunch of in-house developed tools that are dependent on a bunch of third-party open source libraries, right, that are developed by a bunch of in-house devs. So functionally, prod trusts those in-house devs and open source tools to be safe and secure. And that creates a clear path of potential compromise between, let's say, an irresponsible third-party dev or in-house dev and third-party library, and potentially the production environment. So the root of what we're talking about is that because of how trust relationships can be chained, they allow some significant potential for lateral movement and exploitation and escalation of privilege. And specifically, for the most part, we're talking about in agile development environments, very much like you see in kind of startups and popular web properties and those kind of things. So let's take a real quick look at what these environments look like. So networking is hard, right? So these environments look a lot like any other environment when we start out. So they have workstations like anyone else. They have general user access. They have admin backbones. They have a couple unique things, right? So they have things like local and remote development environments. We have CI/CD pipelines. We have multi-tiered environments like staging, prod, remote dev. And we also have the entire burden of, let's say, the DevOps tool chain to maintain and manage the development infrastructure that supports these developers, right? So when we look at this like broke down, you can see that we have, say, our average agile development startup. We have a user laptop, and they have a local dev environment with some VMs and mounted file systems. They've got a wireless router that they connect to and can get on the internet. And they connect out to some third-party applications in a cloud environment. So they've got some Git, a variety of probably third-party SaaS applications, maybe some G Suite, some HR applications, et cetera. And then something like AWS, Azure, Google Compute. And then behind that, an infrastructure that's probably multi-tiered, right? So development and staging, production. So development and staging being where we integrate the code and where we work on the code. And then we're going to have a variety of things, right? We're going to have Jenkins and other continuous integration like Travis. We're going to have Chef or Puppet. We're going to have a variety of different servers that serve different purposes. We're going to have some integration and deployment pipeline into production that should have the minimum number of assets required. These should all be heavily protected systems that are serving the primary business line systems for the organization. So things like the primary web servers, the primary application servers, the production databases, et cetera. So what this boils down to is attacking these environments. Why is this novel? Why is this different, right? Traditionally, when attacking a standard Windows environment, it's compromising an individual system, replaying credentials, getting a hold of compromise of the central authentication mechanism, and then spreading through everything, right? These are a little different. There is some exploitation of central authentication on occasion, but it doesn't necessarily always yield the windfall exploitation that it would in like a Windows environment. So what are we looking at? Looking at exploitation of individual developers. This tends to be massive, right? So very often, it'll vary from dev to dev. One dev may have nothing. Another dev may have access to everything and deploy rights, right? So it's very individual user role focused. Compromise of CI/CD tends to be game over in many cases because very often automated users like Jenkins, et cetera, have the ability to do deploys to critical systems, and you can modify code as it's being processed by the CI server, and so you can actually inject kind of some unexpected artifacts and stuff into these code. Also, it tends to be a hotbed of secrets and access. It also tends to have a bunch of extra open ports and those kind of things. So pivoting and lateral movement tends to be more reliant on individual user function, like how we're going to move through the environment. And it tends to be a lot easier when you can compromise code that is used through the environment rather than an individual workstation or system. And then local versus remote development, right? So a remote development environment tends to be the Wild West. It's very exploitable, but doesn't always have that wealth of secrets and information you want unless they're shared with other environments. While a local development environment, while they tend to be more locked down usually than a remote dev environment, they have the opportunity of being significantly worse because if the configs aren't correct, it can expose a bunch of unnecessary ports, exploitable services, and then sometimes there's some ways to bridge connectivity or pivot into the host operating system. All right, so we talked about this in theory, so I'm going to talk about some kind of realistic examples. Right, so the first is we're an attacker, and we compromise a developer's laptop. So we get on this developer's laptop, and through them, we're able to compromise Git and Jenkins. We use that, we backdoor some test cases, and we compromise the Jenkins CI server itself. It can push code to a variety of places, and it has executors slaved to it. So executors do builds for the Jenkins server, and they tend to be other systems. They could be dedicated servers, or they could just be multi-use systems that tend to have additional available resources. Because we have control Jenkins, we can push arbitrary code to all these executors. So now we have C2 of all the executors that are paired, and anything that is pulling code from the CI pipeline. So from there, we can inject whatever we want, and we do. We compromise some executors. We eventually get on a system that allows us to write directly to the chef repo. We modify the chef repo and add some data bags and cookbooks. And in one of those cookbooks is a reverse shell recipe. It turns out this is that invalidation of trust, is that production environment was actually getting its chef configurations from the chef in staging. So because of that, we were able to push reverse shell recipes to each of the production systems when they checked in and get reverse shells out of prod to us and have bridged that relationship between staging that was supposed to be relatively restricted into the production environment and take control of the entire production environment, right? So another example, so we compromised dev laptop, compromised Jenkins and Git again through being able to push some test cases and those kind of things. So we find that what's happening is these builds are happening, they're being pushed to kind of an enclave that's supposed to be like a clean source area where things are going to be checked through and gone, they're going to be manual code analysis and these kind of things. But there are a couple that don't go through as rigorous detection. And they get pushed into this secure enclave that then gets reproduced into prod and some more secure staging environments. So even though we couldn't route traffic directly, we were able to backdoor some of these code repos and tests. And then when the builds were ran, it actually pushed our code and deployed it into the environment, and we were able to then affect those production systems without ever routing a packet to them. And most of this was through like unit tests, right? But for the most part, many developers won't really have a problem with it. If the test passed and everything looks good and there's no errors, hey, great, let's move on, right? So with that, the point with all this is that we did this a lot manually, and it's pretty frustrating, and you have to tailor everything to everything you're doing. So Clint happens to be a very skilled developer, and well, he can write better code than I can for sure. And so we put our heads together, and he wrote a tool called Gitpwned, and I'm going to pass off to him to talk about it.
All right, thank you, Noah. I told him not to say that, but he did anyway. All right, so we found ourselves in interesting places a number of times on tests where we manually backdoored some things, and we thought it would be nice to automate this a bit, both to make our pen tests more effective, as well as sort of to share with the community. So before I get into the specific architecture decisions we made, let's take a step back and just very simplistically look at command and control, or C2 in general. So in the very simplest case, you have a server, which is sending commands to one or more machines you've compromised, which then runs those commands and then sends the results back. Fundamentally, this is the core of what command and control is. So maybe if you want to be a little bit tricky, maybe instead of using HTTP, use IRC, DNS, or try to obfuscate in some other way. So traditionally, defenses have focused on either things on, say, host machines or on network. So on the host machines, sometimes defenses will look for agent-like processes. So is there some process that's spinning up every 60 seconds or 5 minutes and doing a set of actions and then stopping, regardless of what user activity is happening on the system? Or perhaps they're looking for unusual behavior. So is this accountant laptop suddenly trying to SSH into a bunch of machines or port scan? Or maybe it's accessing sensitive information that normally it shouldn't need access to. Or on the network side, is a machine talking with unknown hosts or IPs that it shouldn't be? Or perhaps looking at traffic contents itself for malicious activity. So we knew when we were designing the system, we want to communicate with trusted network parties, some network endpoints that the machines should be talking with, or it's not unexpected. And we also want to mimic user behavior so that we don't appear like an agent that just is running unconnected to user behavior. Okay, so just explicitly talking about some of our hashtag goals. Just typical command and control, we need to be able to send commands and get the results. We need to communicate via trusted party. We want to mimic user behavior. And as some sort of sub-goals, we want to limit forensics. So if someone notices something sort of fishy, we want to make it hard for them to figure out exactly what we've done and how we're operating. And as a practical note, we also want to limit the blast radius, right? So if we're doing a pen test for a specific company, we don't want to compromise someone from another company, because that would be bad news. All right, so simplistically, let's say we have an initial foothold on a machine, say Joe Dev. How we get this initial foothold is sort of out of scope for this work. Maybe we did spear phishing, maybe we got them to run some code we backdoored, however. So simplistically, we might say, okay, we have a server, let's just send commands and get results via that. But again, it's unlikely that these machines will have a prior relationship to talking with us. So if we do that, it's like, hey, why are these machines talking to this external machine that we don't trust? So we can't do that. But if we step back and think, okay, so developer, what do developers normally do? Oftentimes, developers are using open source libraries that's hosted on GitHub, or perhaps their company's code is hosted on GitHub, or maybe they just have personal repos that they're working on. So many developer machines, it would be not surprising to see them communicating with GitHub. Right? So if somehow we can use GitHub as a command and control platform, this would fulfill the goal of communicating with a trusted party. Okay, so how are we going to do that? So again, we need to be able to send commands and get results back. So what are the types of things that GitHub will allow us to host? So we can make gists, or we can have Git repos, and there's probably a handful of others, but these are the main ones. So we could have our attacker server create a gist with commands, which then is pulled down by the compromised machines, and then they create gists as sort of a result of those. However, in terms of sending commands to a specific machine or being able to easily collect all of the gists with command output, that might be a little bit difficult. And also, it's not common to be creating many gists and reading from them. So behavior-wise, this might look a little bit anomalous. So let's not do that for the main command and control mechanism. Let's instead use Git repos. So if you think about it, we could commit commands into the repo, which are then Git pulled down by the compromised machines. Then they run the commands and then commit them back into the code and then push them to our repo. So what we end up doing is having a malicious command and control repo hosted on GitHub. And we'll talk more about this shortly. Okay, so that's how we can do command and control. But again, so the fourth goal, how do we limit forensics? How do we limit blast radius? We can do a reasonable job at this by just making it a private repo. So now only people who we give permission to read or write this repo, only they will have access to it. Okay, so that does that. And okay, so we still need to mimic user behavior. So if you're not familiar, there's a number of in every Git repo, there's a .git folder, and it has a bunch of files in it. So for example, a config file, which has branch information, origin information, user settings, things like that. There's also a directory called a hooks directory. And so what a Git hook is it's basically an arbitrary piece of code that runs whenever a user is doing a state-changing Git action. So for example, the pre-commit hook, if you run git commit and then right before it finishes committing, it'll run this arbitrary pre-commit hook, which can say, make sure to specify a descriptive message, or make sure that your code fulfills various coding standards, things like that. So the important part about Git hooks is it has two important properties for us. One is that Git hooks are not in version control, so we can arbitrarily modify them. And if the user says git status or something like that, unless they're specifically looking in the Git hook folder, they won't see any change. right? And then the second property is because each Git hook happens as a result of user behavior, basically by modifying them and putting malicious behavior in a Git hook, when a developer goes about their normal development tasks using just standard Git commands, we're basically tacking on additional functionality that happens after it so that to a certain monitoring system it looks like, okay, so they're just doing normal Git workflow, and then just a couple of other things are happening as well. So that fulfills our goal of mimicking user behavior. So rather than running every 60 seconds or something that's very agent-like, we're instead sort of tacking on to standard user behavior. So just a quick summary. We're using GitHub to host the command and control. A private Git repo is the transport layer. And we're using Git hooks to mimic user behavior. OK, so that's a lot of text. We're going to do a bunch of diagrams that walk through it. So there's 4 primary steps. So first, some initial reconnaissance, then setting everything up. Then we're going to establish persistence on an initial machine, which has an initial bootstrapping and then running the agent. And then we can spread across machines and environments. OK, so let's say, again, we have this initial foothold on Joe Dev, and we're wanting to figure out, what is this company's development environment like? What languages do they use? What frameworks do they use? What would make sense to be on a machine for this specific company? So maybe you look at their GitHub. If they have a company GitHub, you're like, oh, what is all their code written in? Or in this case, we can also look at one of their developers. So let's say we're looking in their code repo, and we see Disruptor, which we just happen to know is their primary web app. Because this company is based out of San Francisco, and they think that disrupting is too slow, and they want to disrupt disruption and make it even more disruptive. So that's the company we're targeting. And so we look inside it, and we see a manage.py, urls.py, and requirements. And we look at the requirements, and we see Django. So we think, oh, great. The primary web app for this company is Django. So they're probably a Python shop, and they probably use Django. So the second step is we want to choose a popular open source repo that fits into this framework, into this environment. So one Python example would be IPDB, which is a popular debugging library. So now we know 3 important things. 1, we know the language and framework of this company. 2, we have an open source library that makes sense in the context of their company. And 3, if this company is based in San Francisco, their developer probably looks like this. OK, so let's talk about the setup process. So first, we're going to create personal access tokens for 2 different GitHub accounts, a primary and a secondary one. And we're going to talk in a second about why 2 and not just 1. And then we're going to run this setup script. So what does the setup script do? So first, it's going to clone this popular repo that you specified onto your server. And then it's going to basically copy, or it's going to clone that and push it into a private repo that we control using the primary account. So the primary attacker user is the owner of it, as well as a bootstrap gist, which has commands which sort of will set up a compromised machine. And so we need to give an unknown number of parties both read and write access to this repo, and we don't necessarily know who they're going to be ahead of time. So how do you give access to people to a private repo without necessarily knowing who ahead of time? So that's where the secondary personal access token comes in. So in the bootstrap script, what we do is essentially include that in the bootstrapping file so that anyone who is pulling down the bootstrap file using this personal access token, they can basically show it to GitHub and say, hey, I have permission as this user to access this repo. So that's how we're able to have compromised machines have access to the commands we're trying to give them, as well as get the payload content back. And if we just use one account, then if, say, someone's doing forensics and then they get this primary token, then they could potentially delete our repo or do anything we can do. So it's sort of a principle of least privilege thing is why we're using 2 accounts. OK, so let's quickly check in. Where are we? So we know the target's primary language and framework, so they're using Django. We've chosen a popular library that fits into there, such as IPDB. We've mirrored that popular library in a private GitHub repo. And we've created a private gist, which is going to bootstrap the process. So let's talk about establishing persistence on a compromised machine. OK, so JoDev has this internal web app, such a disruptor that belongs to the company. So what we're going to do is we want to insert sort of a one-line backdoor script such that whenever someone runs it, then we backdoor their machine and set up command and control on it. So we'll just represent that by this little red line. So we want to put this backdoor one-liner somewhere that's run often, but is perhaps not as well vetted as other places. So maybe somewhere in a test suite or in a build or a configuration file, something like that. So specifically, let's say in this disruptor, there's like a test folder, and we put this one-liner in there, which is going to set up the bootstrapping process, which is essentially just curling the gist we set up and then piping it into Python. So it's just a Python script. So when the test suite is run, either by us or by Joe Dev, it's then going to curl this gist and then run it. So this is the setup process, or the bootstrapping process. So first, we're going to find where we're going to clone this command and control repo down. So we want to put it someplace that's normal. It's not unexpected for it to be there. So we look at the default user Python library install folder. So all of their other Python libraries are there, and we just add another one. And again, we're mirroring a very common one, so it's not unexpected for it to be there. So after we find where we're going to put it, we then clone the repo down and put it into site packages, so our malicious IPDB. And this repo also has an agent file. So the agent file is responsible for every time it runs, it's pulling down the latest commands, running them, committing it to the repo, and then pushing it back. So it's sort of doing the main agent processes. So we take this agent file and copy it into a Git hook in this command and control repo. So again, if someone goes there and runs git status, nothing will be different than the default benign repo that we're mirroring. So after that, we've installed the agent file, but we need it to run periodically. So how do we make it run? As mentioned previously, we create a series of Git hooks in this disruptor repo. So as the developer is just committing code, running git pull, or pushing, things like that, our agent will be running in addition to the standard Git functionality that they expect. And again, after we're done, we basically change the remote from pointing to our malicious command and control repo to the benign one. So now if someone were to look at this at a point in time where we're not actively doing something malicious, it's going to look totally benign. And then finally, we're going to run the agent itself. So let's just quickly walk through that. So this is sort of the state of the world. So the first step of the agent is going to switch to pointing at our malicious remote, which is then going to pull down any additional commands. So commands are basically just defined currently in this payload file, which is just arbitrary Python. So maybe you're, okay, grab the current user's username or MAC address or get all the environment variables. Basically anything you want the machine to run, you just put in this arbitrary Python file. So the compromised machine is going to run all these things and then commit them. And then it's going to push the results back to our server. And it's going to generate a node unique ID. And it's going to push into that branch to basically so the reports from different machines don't collide. And then we set up a GitHub hook so that whenever there's a push, we automatically hear about it on our attacker server, and we know that we can run pull and extract the information that's been sent. And then finally, after we've got them to run our malicious code and extracted it, we then again, make every reference to our malicious command and control repo disappear and point back to the benign one. So again, if you look on disk, everything looks great. Okay, so just quickly spreading. So it depends on the company. Everyone has a different SDLC, but often there is a develop branch that is not very well vetted. There's sort of a constant flux where people are developing feature branches and then merging them in, or taking develop and merging into their feature branch so that it's not a huge merge conflict when they try to merge it into, say, a QA version or something like that. So the first step is to find a branch that's less well vetted, and to push into internal code hosting or some sort of continuous integration tool like Jenkins. So now our malicious one-liner backdoor is now there. So let's say there's another developer, Alice Dev, no relation to Joe. She may have access to repos that Joe doesn't, or access to other internal systems. So when she is developing and she runs git pull and she's like, okay, I'm working on this feature, let me merge and develop, and then runs the test suite, she gets compromised and then we can send her commands as well. And then perhaps there's a DevOps person named Bob who can SSH to prod for troubleshooting, create release builds, write access to Puppet Chef, things like that. So similarly, when he pulls down that repo and runs the test suite, he is also compromised. So if our goal is to get into production and we compromise someone who can get into production, then we've achieved our goal. So here we're exploiting, as Noah was talking about before, trust relationships between developers, between employees. But we can also attack trust relationships between developers and, say, continuous integration. So if the Jenkins server automatically runs test suites, we might actually backdoor that in the process of doing this. And then if Jenkins has permission via some deployment process or get pull to send to staging or production, then we can then compromise production that way as well. So there's a couple of different avenues there. There's a number of useful features, but there's a bunch that we would like to have that are not there yet. Currently, the exfiltrated information is encrypted in transit in that it's going over Git. However, it would be nice to encrypt things client-side to make forensics a little bit more difficult. We would like to integrate with other version control systems like Perforce or Mercurial. Currently, only Git is supported. And it would be nice to have some specific target modules for continuous integration, continuous deployment platforms like Jenkins or Travis. And also just more modules for common reconnaissance or exploitation tasks would be nice. Okay, so in summary, Gitpwn is a tool for penetration tests that lets you do command and control using a private Git repo on GitHub. It's flexible, so commands can be arbitrary Python. We mimic an arbitrary public Git repo that fits into the environment, so it's stealthy in that respect. And it's also very easy to set up the bootstrapping process so that it's tailored to the target environment. One thing we found on real penetration tests is every environment's very different. How the SDLC works is very different, and having a tool that always works in a certain way tends to make it less useful. So we try to make it as flexible as possible so it can be tailored to a given project. Again, this is targeted primarily at agile development shops, and it was written to highlight the potential risks of mismanaging trust relationships in an enterprise. Okay, so there's many moving parts, so we ended up recording the demo. So first, let's look at the setup process. Okay, so we're in the Gitpwn repo, and there's a config file which basically says, here's the repo I want to copy, here's a couple of personal access tokens, and then here's the attacker server that I want the Git hook to point to. So basically, once you have that information, all you do is run the setup file and you pass in the config information, and then it does a bunch of things. So first, it's cloning down the popular repo and then pushing it into a private repo. And then it's setting up a webhook. It's adding the secondary user as a collaborator to the first one. Don't try to read all of this. There's too much. I'll show you in a second all the things that it did. But one important takeaway from at the end of it is basically it will output this basically one-liners, which then you can use to backdoor a target repo. So if we look at what exactly this gist content is, it's basically a Python script that does the bootstrapping that we explained in the architecture diagram just a minute ago. So let's see. So this is on the right. That was the official IPDB, and this is our private one that we just generated from the setup script. As you can see, so there's like a similar number of commits. A lot of the history looks the same. There's a bunch of collaborators, and it looks pretty much identical. We can see that the secondary user has been added as a collaborator, so they can write. And there's a webhook that points to our attacker server, so that every time a compromised machine pushes, we see it. Okay, cool. So that's the setup. So how does this work on compromising a machine? Okay, so again, we're on Joe Dev's machine. We have inserted the backdoor towards the bottom there. So now if we run the test suite, it's basically going to pull in the private gist, which is doing all the bootstrapping. Just to make things clear, I had it output debug info. So we can see we added a bunch of Git hooks, a pre-commit, pre-push, and things like that. And so each of those hooks we added are basically calling what looks like a sample Git hook in the command and control repo, but again, it's actually our agent code. So where is this command and control repo? So if we go there and then look in the directory above it, this is where all the default Python libraries are. So look, there's a bunch of them, and we're just one of those hiding in plain sight. And then, so let's look at git log. This is just what the default benign repo has. If we run git status, we're just on master, everything's great. If we look at all the remotes, we're just pointing to where we should be. We look in the git hook directory, like, oh, maybe something bad happened there, but it's just a bunch of sample files. However, one of those, again, has been rewritten to have our agent code there. So that's that. Oh, and then if we look on the attacker server, we automatically got the webhook and extracted the information. So now this is the result of running our arbitrary payload on Joe Dev's machine. So we ran ifconfig, we got their username, we ran the processes running, and things like that. So currently there's just like a couple of example payloads, but really anything you want to write would be fine here. Okay, so finally, let's see. So we've backdoored the test suite. Maybe we're using develop or some branch that is constant in a state of flux. We're going to commit this to the repo and then push it into the internal code hosting, which in this example is a separate GitLab instance in the AWS dev environment for this example company. So if we go to GitLab, we refresh, we can see the commit that we just sent. And based on this company's SDLC, basically they, every time there's a push to GitLab, they automatically run the test suite using Jenkins. So if we look at the console output for Jenkins, we can see there's the test suite running that we backdoored, and then we can see this additional text, which is cloning down the command and control repo, running the agent, and things like that. So again, if we look at nodes, now we can see that we did run arbitrary code on Jenkins, the continuous integration server, and here's a bunch of the environment information and things like that. So if in this company Jenkins has permission to push to prod, we can then send it arbitrary commands, which then push to production as well. So again, this is sort of a very quick minimal example because of time constraints, but on both Joe Developer as well as GitLab, we are running arbitrary code, so your imagination is the limit here. All right, so let's go back. And to talk about mitigation for some of these attacks, I'm going to pass it back to Noah.
Thanks, Clint. All right, so we just talked about some potential issues and problems and showed a tool that takes advantage of some of these potential issues and highlights the risks. So let's talk about ways we can potentially fix it. So anytime we're looking at potentially mitigating a problem, we need to understand what the root causes are here first, right? So one of the main ones is that development security just has not kept up with the speed at which these very skilled, very rapid moving development shops have grown. We have startups that go from the first line of code they're writing to like GA releases in under a year sometimes, and that's just a massive amount of change, right? And at the moment, development security processes, procedures, and even some technical controls just have not been given the focus to keep up with this, right? It's just something that hasn't gotten the attention. Security and development tend to be separate silos, so that means there's an absence of collaboration very often, there's an absence of visibility into what's actually going on, and very often leads to some misconceptions about what levels of security and protections are actually in place, right? And the last is incomplete technical controls. I know this is a big one. I mean, a lot of the security problems we deal with in security research on a day-to-day basis are because of incomplete technical controls, right? But nonetheless, it persists. So examples would be maybe we punched a couple extra holes in a firewall, or we scoped some secrets to a much lower level user than was necessary to make things easier, things like that. So there's a couple different ways. There's processes and procedures, and then there's technical controls. So let's talk about processes and procedures first. So first is that as far as a process goes, doing code review, doing code collaboration, and reviewing commits is necessary. Like obviously there's a limit because of scale, but having automated processes in place to help with some of this will, even though it won't solve these problems, it can help. right? Another is defining a real development process. And I don't just mean telling your devs how to do the development. I mean working with them to find out what their constraints are, their requirements, the technologies, and all the things that they work with on a day-to-day basis, because this is where they live, essentially, and helping them create secure, reasonable constraints, sane ways of developing that meet their needs and don't impede their ability to do their work, right? And even though that sounds like a magical unicorn, it's totally possible. So reviewing development and staging security controls and their environments on a regular basis is also important, because these are areas that are in really large states of flux, right? As we add new controls, as we patch, as we update, as we change. And we do change management already, so keeping a good eye on this from the get-go gives us a lot of insight into what we need to be planning for and the types of risks and things we need to be mitigating, what we might be exposed to. Okay, so we talked about processes and procedures. Let's talk about real technical controls. So first is like SDLC, right? Having your SDLC clearly defined, set up, and designed in a way that is strong and doesn't expose you to a bunch of undue risk is really hard to do, but it's possible. So sandboxing CI processes, right? Creating those pre-existing kind of development environments and sandboxing CI processes helps prevent things like shelling Jenkins via test suites, right? I can count the number of environments I've seen that actually sandbox all their CI builds, probably on one hand in my last 2 years of pen testing, right? So examine not just your GitHooks, but all of the code as infrastructure things that require and control and set up your development situations. And then also doing some type of configuration enforcement on that, automate configuration enforcement with like Puppet, Chef, these kind of things really goes a long way. Host-based monitoring and logging and alerting, looking specifically for malicious development and exploitation of developers goes a long way, specifically in an environment like an agile dev shop where developers are really your highest potential point of failure, and they're the group that is technically making the most money, right? Because they're generating the product that your business is staked on. So not only should they get the most attention from the point of view of protecting that asset, they should get the most attention because they're going to need help to be able to do their job securely and in a way that helps the entire company be successful, right? And then network segmentation. This is old school, tried and true, right? Reviewing and enforcing network segmentation, not just on a point of view of port and IP, but also on system and code tenancy. So where do my systems live? Where are my bridge points? Which systems are multi-homed? What code transit trust zones? And am I using something like clean source? So clean source is a concept that any code going into an environment is as secure and safe as the environment it's going into, right? Really, really hard to do, but these are kind of the things we need to think about when we're talking about these type of exploitation scenarios. All right. So at this point, we're going to open it up for questions. I think we have a couple minutes for that. While we're taking questions, we're going to leave our contact info up. And if you don't get time to ask us a question, we'll go to the wrap room afterwards, and we'll have a little more time if you need to. Thank you.
Yeah. Thank you for your time. Hi, yes.
Your example with Django, what platforms and libraries does Gitting support?
Okay, so the question was, the example was Django, and what languages and platforms does it support? So currently the backdooring and agent code is written in Python, but that just means the machine that it's running on needs to also have Python, because just to like get the bootstrap process running. But you can also say it's a Ruby on Rails project, or really any language. You could just do a shell exec, pipe in the bootstrapping gist into Bash or something like that. Basically, as long as Python's installed on the system, you can shell out to it in any language and framework. So I would say it's agnostic in that respect. So, thank you.
Mac agnostic.
Yeah, any other questions? Yes.
One part of what the purpose of this is to avoid detection, behavioral detection, because of feedback to the user. How do you avoid detection of the commands you send? You avoid detection of getting the commands, but executing the commands. How does that feedback the user behavior or not be detected?
Yeah, so that's a great question. The question was, we've taken a lot of steps to try to avoid detection. in terms of like being recognized on disk. How do we prevent being recognized the actions themselves? So if, say you have some sort of host monitoring system that's looking for attempts to dump the keychain or do something that might be bad, just because we're running the commands in a stealthy way doesn't mean that someone looking for that isn't going to see it. So if a command that you would run would get detected normally, this doesn't make that part better. That's sort of the fundamental limitation of what they're looking for on the host.
Can I add something?
Yeah, please.
So to caveat that, so ultimately any like advanced monitoring, logging, alerting is going to catch plain text commands. We were talking about potentially adding some encryption to kind of additionally protect things being passed, but ultimately it's going to be in clear text at some point. This is a cool tool for showing these exploitations and doing the exploitations and automating some stuff, but what it doesn't ultimately do is replace the skill of an attacker, right? And ultimately, when you're attacking a dev, and something that I've had to learn through a lot of stuff is that when you're attacking a developer, you have a lot of leeway to be within the context of user behavior and still do a lot of really powerful things. Very often, you don't need to dump the keychain. Right? You can do very simple behaviors built on how their current workflows are. For instance, very few devs actually password protect or passphrase protect their SSH keys that are used for, say, committing to code repos and those kind of things. And a commit looks relatively mundane, right? So we can do a lot of things spread through environments and get to those critical points without necessarily doing things like dumping keychains or things that are going to get us caught. So, but understanding the type of environment and the person you're looking at, who you're compromising, really important. So one of your first things you should do once you get on is take some time and log outputs and then review the behaviors that are taking place, looking at their bash histories and these kind of things, looking at their Git histories. You can take that and then create your exploitation method and what chain you actually need to follow. And by creating kind of a tolerance of how likely is it they're going to catch on these different things, you can decide what's worth it to try to actually do, right? So and that's a long way of just saying that the tool does not replace the skill set, but the skill set can really enable this tool to do really cool things. Answer your question, Andy?
Yeah, thanks.
Yeah. Any more questions? Yes, sir.
So companies got like a private Git repo as opposed to using GitHub. How would you log those things?
Sure. So the question was, if a company uses a private Git repo, and by that do you mean like they host their own Git server? All right. So in the case of they're hosting their own Git server, inevitably you have to know that it exists somehow, whether that can be via social engineering or reconnaissance or anything like that. Once you find out and get initial foothold in a system, as long as they can talk out to public Git, you can get that initial command and control, find out the location and targets that they're using, and then modify the configs in order to then use that Git repo or that private Git server as any component of the exploitation chain that we're talking about, including if you get significant privileges, you can actually turn that into your C2. Like into your actual C2 server.
Yeah, so GitHub is used as the command and control mechanism, but their internal Git repos can be hosted anywhere. So it could be private GitHub Enterprise, private GitLab, Gitolite, it doesn't matter. It's just sort of the mechanism of propagating the initial backdoor, which as long as you use Git, it works the same. Yeah, great question.
I think that with that we're out of time, but if you guys have additional questions, we'll move over to the wrap room. Thanks.
Yep, thanks again.